Hey, what's up, guys? This is Chung here. And so this time, let's take a look at another LeetCode problem, number 1383. Maximum performance of a team. Okay, so you're given like n engineers, number from 1 to n, and the two arrays, speed and efficiency. And right, and you need to, and then another one, k. K is the number of a team. You need to find a team with a number, a team with person number of equals to k, whose performance is maximum. So how do we calculate the performance? The performance equals to the total speed of all the numbers of all the peoples in the team plus the minimum of all the team members' efficiency, right? For example, here, if you have a k equals to 2 here, which means we need to form a team which have two people. And so we pick the engineer 5 and 2, whose speed, the sum of speed is 15, but the performance is the minimum of all the team members. And in this case, it's 60. And in this case, it's total speed is 17 times the minimum of the efficiency, which is 4, right? So So for this kind of problem, right, how can we come up with the solution, right? I think at the beginning I was trying to use like, I think it's kind of clear that we need to use some greedy algorithm here, right? Because at the beginning I was thinking of, can I can I just every time, right? I always pick the best option because for the greedy algorithm, the idea of the greedy algorithm is the every time we always pick the best options at the moment, right? So I was thinking, can I always pick the best, right? At the moment, let's say if we can so in that case, we only need to do it k times, right? So at the first time we pick the best workers, then the second one is we pick the once we remove this worker from this our arrays, can I try to pick the next best workers, right? But then it it seems like it didn't work, right? Because the latter, because the efficiency, right? Although the performance, the speed can be summarized, but the efficiency is not guaranteed because the efficiency it's bound to the minimum value, right? So basically what it means is that, so even though we picked the first one, we thought it's a best answer, but the latter one, the people who join the team later may downgrade the previously result, right? So that for that reason, we cannot just every time we pick like the best answers and we only pick it k times. That won't work, right? So if that won't work, so how about some other ways so to solve this problem, right? So uh, uh, a common thought is, if we don't know, right, how to, if we don't know like which one is the correct one, then we try all the possibilities, right? I actually this problem is very similar as the other one. I think there's like another problem, uh 800 something, 857. I think a similar one. You need to calculate the minimum cost to hire a worker, right? On that problem, you're also given like two arrays. I think the first one is the wages, second one is the performance, something like that, and you need to calculate what's the minimum cost of hiring a worker, right? So similar concept here. we have a case number here, right? Basically, we try all the possibilities, but how do we try it, right? We have to try it from with a sequence, right? So the sequence is we sort the efficiency from highest to lowest, and then we'll be using a priority queue to to track the case numbers of speed because at one time we can only have uh, case people in the team, right? And we want to we want to track the highest of three speed at the moment. And actually sorting by the efficiency here, since the our final result will be bound at the minimum efficiency, right? Since we're looping the efficiency from the highest to the lowest, this is also kind of like greedy concept here, right? Basically, at each time we always try to see, okay, with the current highest efficiency, can we get a better result, right? Basically, that's the idea of this problem, and then let's try to code it, right? So first we're gonna define like a mod for our final result, right? That's the 10 to the power of 9, right? To the power of 9 plus 7, right? And then let's have an answer here. And let's do a current speed, right? Current speed, total speed. How about that? Total speed hmm to 0, right? So what do? We do also a priority queue. Sorry, yeah, we need a priority queue to no queue priority queue to keep track of the our current uh, speed, our current best speed, fastest speed. Mm, yeah, and for efficiency and speed, right? In zip, let's sort this people with their efficiency, right? Zip efficiency, right? Efficiency and speed sorted. Yeah. Mm, and let's do a reverse. Reverse equals to true, right? Because we want to do a greedy algorithm here, right? Every time we always pick the highest efficiency, and we'll see with with the current highest efficiency, what's the maximum speed we can get, right? And then we will try to see if with that combination, uh, if we can get a better result, right? Then the priority queue dot sorry heap heap queue dot heap push, right? We push the current speed to that, right? And then we do a what? We will uh, plus speed, right? And then if if the length of the priority queue is greater than k, right? So that means with the current speed, let's say there are more than case people in the group, we just discard the 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 worst worker, right? Mm. So we just discard. We discard the we do a heap pop, right? And do this total speed, right? We discard the slowest speed from the priority queue, right? We do a heap queue dot heap pop, right? And then priority queue dot stats, right? So because once we after we abandon this one, there will be like we also need to remove it from this current speed, right? So that we will have like this current total speed for the current for only for k people, right? And then in the end, we just simply check update this thing, right? If whichever is bigger, right? If this one is bigger or the current total speed, right? Times the current efficiency, right? Then in the end, just return answer uh, mod is mod, right? Yeah, I think that should work. All right. Uh-oh. Let's see. I think yeah, I think I made a mistake here. So 10 to the 9. Yeah, cool. So this approach works, right? Let's take a look. So see why this thing works, right? And let's say, this sorting by the efficiency kind of makes sense, right? Because we want to try, we greedily try the best efficiency at the moment, right? Meanwhile, we're also maintaining like a priority queue for the top three speed, right? And let's say we add like, let's say we have the current worker is the k plus 1, right? Workers. So after adding this worker to the heap queue, right? And we'll be removing the smallest, and then we'll be using that thing to do another check, right? So let's assume the one we just added is the worker. What does it mean? It means that the the speed is like is the smallest, it's the slowest speed, right? In that case, so after we push this speed to the heap queue, and then basically we'll pop the same speed out, right? Basically, this current total speed will not be changed. Let's say the current one has the slowest speed, right? And then in this case, it won't affect our final result, right? Because then it means that the previous employee can give us like a better result, right? Because the previous employee will have like a higher efficiency, but with those three employees, we'll also have a higher total speed, right? That's why we do a max to compare with the previously result, right? And with the current one. In this case, even though this thing is not accurate, I think so. In this case, the current employee is basically the efficiency is the current employee's efficiency, but the current total speed is still using the previously previous speed for the previous workers. So this thing is not like a very accurate result, right? Because the current total speed and the current efficiency doesn't match each other because the total speed was uh, was uh was made of uh previously was made of previous like workers, but while the efficiency is from the current worker, right? So this is plays a little bit confusing here, but it won't affect our final result because in this case, this thing will never give us a better result, right? Because this thing doesn't change, right? But the efficiency uh, is is lower at this moment. So this thing will always be smaller than the previously answer. So that's why this formula will work. It can guarantee us it won't have any unexpected uh, higher result, right? Because we are sorting by the efficiency. Okay, and I think that's pretty much everything for this problem. Basically uh, first we use a greedy algorithm here. Basically, we sort the workers based on the efficiency because the final performance is bound by the minimum efficiency here. That's why we sort by the efficiency and we process the workers from the highest efficiency to the lowest one. And and then we just use a priority queue to store to store to maintain the top three, sorry, the top case speed, right? And then in the end, we just simply check if if this combination can give us a higher result, right? This is the key point. Basically, we try all the possible workers. Basically, we try all the efficiencies, and then we just maintain the top speed here, and then we just do this over and over until we process all the workers. Okay, cool, guys. I hope you guys enjoyed watching the videos and try to memorize this kind of like template. You can call it template or like an idea or like or solutions. Next time when you see this kind of issues where like you have two arrays, right? And you have two factors, basically two factors in two arrays which will contribute to the final results, right? And the very common way is that we sort by something, you know, because in this case we cannot sort uh, by two things at the same time because its efficiency is bounded. It's bounded with minimum value, so that's why we have to sort only by the efficiency, and then we just loop through everything, and then while maintaining the top speed. Uh, cool guys. I think that's it for this problem. I'll be seeing you soon. Thank you guys. Bye bye.